the squiggly thing. So just because I'm sick of not having any notation to be able to write with, it's like trying to like write, sentences without punctuation or like the letter E or things like that, right? So it's just I've had enough, okay? So or like this sentence, no verb. Because anyway. So let's remember, how do we do differentiation, right? We said that differentiation was kind of an operation you could do on a function, okay? Just like sine or cos or tan or log or something like that, right? So this is our, what we call the differential operator, okay? When you see that in front of something, like say f, okay, so this is a chisel, I'm not used to chisels. That means differentiate f, right? So that's f dash x. Okay, so that's differentiate, right? So we need some notation for anti-differentiation. Okay, so I'm still not really getting into the full meaning of it, but I just want a way to write down, well, what's the reverse process? Okay, so here's the notation I'm going to introduce, right? It is affectionately called a squiggly thing. If you want to know what it is, it's actually the letter S stretched out. Okay, why is it the letter S? I will explain next term. But that's what it is. Okay. Then you stick your function in there. Now this is important, right? A lot of the functions we've been looking at, for instance, this one, right? I think this started with like dh on dt equals something, okay? And then you got an expression for h, okay? So here I'm anti-differentiating, right? But just like I could differentiate with respect to x, or with respect to t, or with respect to whatever variable I like, right? I also need to be able to say, well, okay, what am I anti-differentiating with respect to? So here, I would have done it with respect to t. That's my variable. There are no x's here, so it wouldn't make sense to have a dx, right? So here, if I'm anti-differentiating with respect to x, I'm going to write the dx here. Okay? Now, anti-differentiation and differentiation, they're reverse processes, right? So in some senses, you ought to expect that here there's division, so here there's multiplication, okay? Now, again, we're going to get into the intricacies of that later, but at least now you know how to write it, okay? So I read this as anti-differentiate f with respect to x. So this is what gives me the primitive function f prime, okay? And I'm going to include my constant in there, so I don't really need to say plus c, okay? Right, so now we can talk about it. Have a look at the sheet that I've given you. Where's my pile? Now, I don't intend for you to do all of this today by any stretch of the imagination, but if you remember, yesterday, I introduced primitives of sort of like rational functions, fractions, and that kind of thing, and they ended up as logs. We looked at just like a couple of very small examples, so that we could anti-differentiate tan. Do you remember that? What is the antiderivative of, what's the primitive of tan?
Minus natural cos.
Yeah, that's right. Sorry, minus cos x plus c. So this is the way that I would write it now, okay? I'm anti-differentiating tan x with respect to x. I suppose I could do it any way I like. I could have had like, tan theta with respect to theta. Does that make sense? See how I'm writing that? That would be minus log cos theta plus c. Okay, that doesn't really matter what my variable is. Okay. Now I want to deal with these rational functions in a bit more detail, because I didn't really address them very carefully yesterday. So have a look at the question, the heading, the table, where it says primitives of form, and you've got all these fractions. Okay, can you see that? That's the side I'm looking at. So don't look at the trig side. If you can see trig functions, you're on the wrong side. Go to the other side. Right, so let's do this nice and gently. Okay, so let's start off with number one. So how am I going to write this? I'm going to write the antiderivative, the primitive, right, of this. Now, I'm going to stick that dx over there on the end. Because I've just got a 1 on the front, it would have been the same thing if I'd written it like this. Dx over, okay? Because it's just a multiplier, okay? It's just something I'm multiplying. But just to make it a little clearer, I think the 1 is more helpful. Right, now, these rational functions, right? Rational in that it's a ratio, it's a fraction. That's all we need, okay? We're sort of anticipating that these are going to lead to log functions, okay? So what I'm looking for is something like this. Just like, yeah, kind of just like this. If I have the antiderivative of this kind of fraction, this special kind of fraction, okay? So this is what we usually get out of chain rule with a log function, right? So if I had to differentiate that, I'm expecting this, log of whatever that is. Okay, does that make sense? You see how if I differentiate this, this is where I will end up. Okay. All right, now have a look at this. This is pretty close, but it's not quite f dash on f, is it? What's the difference? Yeah, I want a 3 up here. Now, numerators are easy to change, denominators not so much, okay? So what I'm going to do is, being that I want a 3 on the top, because that'll mean it's in this format, okay? I'm going to put one there, okay? But since I put one there, I can't just, as we've seen before, multiply by numbers just because it's convenient. So at the same time, I'm going to divide by 3. So there's no net change here, okay? It's still the same thing. It's just like rationalizing the denominator. You multiply by something, you divide by something, no big deal, okay? Now this rational function is in the form f dash on f, so I can anti-differentiate it, right? That 1/3 is not being anti-differentiated, so I just leave it up front, okay? And then this is going to turn into log of 3x plus 2 plus my constant. That's it. Okay. Now you can kind of see if you once you get a bit familiar with this, right? You'll look at this, right, and you'll recognize it's 3 times too small, right? It should be 3 times bigger, right? So instead of writing this step, you'll go straight here after some practice, because you'll recognize that 3x plus 2 is going to stay in there. But to make sure that I differentiate and land back here, I have to have a 3rd out the front. Okay. All right. Let's have a look at the next one. Which one do I want to do? Actually, not the next one. Let's do number 3. Because it's a little more interesting. Three. Okay. Okay, this time you tell me what to do. Right? How am I going to have to adjust the numerator? I want a -2 up there, right? Because that's the derivative of the denominator, right? So if I stick a -2 up there, how am I going to how do I compensate? Yeah, -1/2 out the front. Okay? You do have to watch out with your negatives though. It's easy to screw those up. So I'm anti-differentiating with respect to x, and now it's in the right form, f dash on f. So it's -1/2 out the front, don't do anything to it, and then log of this, plus the constant. Okay, so in some senses this is just like that. It's just that you got to watch out for the negative. Okay. I'm going to skip a few. I don't want, when you guys go back to this exercise, I want you to go back and do the intervening questions. But let's have a look at 9. Because 9 is a little more interesting. We've got this. Okay. Now, you can see it's more interesting, and it poses a different challenge, because it's not just off by a factor. It's not like I can multiply it by 2 or 3 or something like that, and it will turn into the form f dash on f, okay? Because if this is x plus 3, right? If that's our f, what f dash am I expecting of here? What am I expecting? Just 1, right? And you can't just, as we've seen before, like with differentiation and anti-differentiation, you can't just divide or multiply by x's, because that really screws stuff up badly. Multiplying or dividing by numbers, no big deal, okay? X's, you're in trouble, right? So how do I fix this up? How do I get it into a form that's going to work for me? The answer is, well, here I twisted and turned it into something that worked by multiplication, right? Or division, whichever, right? Now, there's another operation I can use here, not multiplication, division, something else that can help me twist it into a more convenient form. Any takers?
Use plus or minus 3 x.
Right, so instead of multiplication division, I can add or subtract. That's kind of, I don't have all that many options apart from that, right? So what shall I add? If I add a 3 on the top, okay? Now why would I add 3? Because I have a 3 on the denominator, right? Because this is going to be convenient for me. So if I have an x plus 3 here, like before, I can't just add 3 because I want to, so I've got to subtract it as well. So this is all still fine, right? These two are still equivalent, okay? Now if I just chuck some brackets around there just so I can make it a little more obvious, right? I can treat the numerator as 2 separate fractions, right? So I can treat this as x plus 3 on x plus 3. So that's just 1, right? And then I've got this part left over, which is minus 3 on x plus 3. Okay? And now this I can deal with. Now, just as a minor note, sometimes you'll see in textbooks or exams, they'll write it like this, which is somewhat naughty because you really ought to be, you're anti-differentiating the whole lot, right? So anyway. What does this turn into? The 1 you anti-differentiate and it becomes x. And this is, well, it's just 3 times bigger than we'd expect it to be, right? We said we expected a 1 on the front. So this is going to be minus 3 log x plus 3, plus my constant. Okay?